expression within your function that you want to integrate. So first thing I want to look at is we can differentiate something like sine of 3x plus 1, okay? Because we can differentiate that using the chain rule. So we can always say that u is going to equal 3x plus 1. So du dx will equal 3. We then know that y is sine u. So dy du will be cos u, because we remember that we can go down our sine and coses to differentiate, and then we come back up again to integrate. Okay, then we can bring them all together, so we'll have dy dx equals 3 cos of 3x plus 1, because we substitute our u in and so on. So we can do that part. Okay, now that means if I wanted to go back the other way, for example, but I want to integrate just cos of 3x plus 1 rather than the 3, I use the same idea, and we can see that these two things are very close to being matching. Okay, the only difference is we need to find a third of it. Okay, and that 3 comes from our amount of a, our amount of x that is in there. So if we wanted to integrate cos of 3x plus 1, okay, all we'll have to do is integrate it as normal. So integral of cos is sine, but then we've got to make sure we times that by 1 over a. You've also got to make sure you remember your constant of integration each time as plus c. So in general, for any expression where the inner function is ax plus b, we'll have to look at other ones where they're not ax plus b. Okay, we integrate as usual, but we also have to take out a coefficient of 1 over a. Okay, so a couple of examples for you. So the integral of e to the 3x, we have already looked at this. We did bring this in slightly last lesson. So to integrate e to the 3x, well, we treat it as e to the x, so the integral is still going to be e to the 3x, okay, but we have to make sure we take out a power of 1 over a, where a is 3 in this case, so we have to times it by a third. So we will have a third e to the 3x plus c. Same with the next one. So ignore the inner function first of all. Okay, so I'd integrate it, imagine it as 1 over something, so we know we've got to go to log natural. So I know that's going to have to become log natural of 5x plus 2. Again, remembering that you're going to need the modulus signs in there because we've done log natural. Okay, but we have to times that by 1 over whatever our coefficient of x is. So in our first one, we did 1 over 3 because it was 3x. So this time it's 5x. So I've got to times that by 1 over 5. So I'm left with 1 over 5 lots of log natural 5x plus 2. And again, I have to remember my constant of integration. Okay, so we treat it almost as if when we did our chain rule. So we ignore whatever that function is. Okay, so for this one, I could pretend it as 1 over u. So I know that becomes log natural u. Okay, when I integrate, I then sub my initial expression back in, but I have to make sure I remember to times by 1 over, okay, whatever that value of a was. It is very, very close to the chain rule, okay, or reverse chain rule that we are going to come to later on. Okay, if I look at the next one, so if I look at 2 sec squared lots of 3x minus 2, well, the 2 is just a coefficient. So what I'm actually going to do is get rid of my 2 from in there, and I'm just going to have a multiplied by 2 outside, just to make life a little bit easier. Okay, well, sec squared, we should know from the ones that you did yesterday. Okay, and we know that these are in the formula book. Sec squared will become tan when we integrate it. So what we end up with is 2 times by tan lots of 3x minus 2, because our sec squared whatever, okay, sec squared expression becomes tan. I've got the 2 from out the front, but have to make sure I remember, okay, to times by 1 over whatever my coefficient of x is. In this case, 3x. So times by 1 over 3, and I get my plus c. So tidy that up a little bit, gives me 2/3 tan of 3x minus 2 plus c. Okay, shouldn't be anything too difficult. Okay, make sure you're being careful when you've got powers. Okay, so when we come to doing something like 3x plus 4 cubed, we have to integrate it as we would do normally. So to integrate, if I imagine, okay, that this is just u to the 3, when I integrate it, I end up as 3u to the 4. Okay, so I treat it in exactly the same way. Okay, sorry, not 3u to the 4, ignore that. I treat it in exactly the same idea. Okay, add 1 to the power, divide by the new power. So it'll be u to the 4 over 4. Okay, and I think of it in the same way. So this, when I integrate it, I use that idea again. So u is just going to be 3x plus 4. So I'll end up with 3x plus 4 to the power of 4 over 4. But I always have to remember, okay, this magic part of taking out that 1 over a. So in this case, I've got 3x, so I'm going to have to times it by a third, and again, I'll have a c. So my final answer will become 1/12 lots of 3x plus 4 to the 4 plus c. Okay, so we integrate it as you would a normal function. Okay, and we can sub in our value of u again, but because it's a full expression, okay, we have to make sure we take that out. Very, very closely linked to the chain rule. Okay, similar idea. Sine of 1 minus 3x. So again, we do exactly the same thing. If I head back to the top left-hand corner again, if I integrate sine, I come all the way back down. Okay, if I integrate sine, I get to minus cos. So this will end up becoming minus cos lots of 1 minus 5x. But again, I've got to remember, I've got a minus 5x in here, so I have to times by minus a fifth, and then I need my plus c again. So minus cos and minus a fifth, I will end up with a fifth cos of 1 minus 5x. Okay guys, so the next one, a third lots of 4x minus 2 squared. Okay, now as before, because we've got a third there, I don't need to worry too much about that because that is just a coefficient. So what I need to think about is my 4x minus 2. So what I'll end up actually integrating is a third lots of 4x minus 2 to the minus 2. Now we'll use what we did before, okay? So we will integrate it as if it's u first. So add 1 to the power, divide by the new power, okay, will leave me with a third lots of 4x minus 2 to the minus 1, all over minus 1. Okay, but we have to remember I've got a 4x here, so I need to make sure I times by a quarter, and then I'll add c on again. Okay, so if I just come back up to the top for a bit more space, so combining that all together, I've got a third times a quarter, and then I've got a minus 1. So that will give me minus a 12th lots of 4x minus 2 to the minus 1, because I've had to add 1 to the power, plus c. Okay, so we integrate it as if it was itself. Okay, so as if it was a u, for example, just integrate it as a basic term. Okay, then we make sure we substitute back in, but we have to remember to divide by whatever our coefficient of x was. Exactly the same idea with the last one. So with the very last one, again, let's imagine that it's u. So if it was u to the power of 12, add 1 to the power divided by the new power would be u to the 13 over 13. Okay, now all I've got to do is do exactly the same as I did before. So I'm going to substitute my 10x plus 11 in as u instead. So I will end up with 10x plus 11 to the power of 13 over 13. Okay, but I always need to remember times by 1 over 10 and plus c, which means I will finish off with, okay, and again, we'll just go back up to the top. So bring it all together, I end up with 10x plus 11 to the power of 13 over 13 times 10 to give me 130 plus c. Okay, so it's all about making sure we integrate first. If you want to write in, for example, these u parts in first, okay, that's absolutely fine. There is nothing wrong with doing that at all. Okay, add those parts in, and then we can carry on through. Right, what I want you to do is have a go at those for yourself now. Okay, so pause the video, have a go yourself, and then we will have a look at them in a second. So please make sure you pause, have a go, and then we will have a look at them. Okay, so e to the 3x plus 1. Sometimes it's worth doing, right, if it was just e to the u integrates to e to the u. So I know that u is 3x plus 1. So this will become e to the 3x plus 1 still, but I've got 3x, so I'm going to times it by a third and add c on. So I end up with a third lots of e to the 3x plus 1 plus c. This one, again, if I just imagine it as 1 over u integrates to log natural u. So this is going to become log natural of 1 minus 2x. It's a log natural, so we have to make sure we have our modular signs. Okay, but I've got a minus 2x in there, so I need to remember to times by minus a half and plus c. So I end up with minus a half log natural 1 minus 2x plus c. Okay, so each time, use u if you need to. Okay, you've just got to remember to work that next part in. Okay, so again, I'm going to pretend this as u to the power of 5. Add 1 to the power, divide by the new power, u to the 6 over 6. So this must become 4 minus 3x to the 6 over 6. But again, my minus 3, so I times by minus a third, and then I've got my constant. So I end up with minus an 18th, because that's my 1 over 6 and my 1 over 3. Lots of 4 minus 3x even. 4 minus 3x to the 6 plus c. Last one, sec 3x tan 3x, just to make it, just to introduce in the integrating, differentiating the other trig functions. Sec and tan, okay, relate to just sec. So sec 3x tan 3x, if I imagine that as sec u tan u, okay, that just integrates to sec u. Okay, so that's going to become sec of 3x. But again, because I've got my 3x, I'm going to have to times by a third and add on my constant. So I end up with a third sec 3x plus c. It may well be easier to make sure you include these parts in each time, integrate them in terms of use. So again, using that substitution. What you have to remember each time, okay, is that you're including these parts, the manipulations, by 1 over whatever our coefficient of x is. Okay.